I think that we can start. So first of all, welcome everyone. My name is Rafael Fernandez. I work as a postdoctoral researcher with the UNESCO Chair in Disaster Risk Reduction and Resilience Engineering. And today we are all here for the webinar titled Simulating 2D Hydrodynamics at 30 meters resolution for the entire planet, who will be delivered by Paul Bates from University of Bristol and Fathom. Before giving him the word, we just want to mention that we have an upcoming webinar in July. With this, we will close the season of webinars, but we will have a new webinar season coming soon that we will share details by email, and you will see in our website soon. But the one that we are going to finalize in July is titled Community Hazard Risk Assessment Tools, Structural Fragility and Vulnerability and System Reliability Mapping. This will be delivered by Dr. Asana Paramal Bateri from the UNESCO Chair and Dr. Ji Yoon Byun from Glasgow University. The idea of this last webinar, and really more than a webinar, will be a course or a hands-on course in which during 2 days the presenters will introduce different methods around the structural fragility and map system reliability at the community scale. So for this, we will send you some preparation kit and different MATLAB Excel files and Python tools for you to work and start familiarizing with it. The idea is at the end of this course, you will have the tools and all the information needed to develop and to implement the different methodologies that will be introduced in this course in July. We will let you know by email, and you are free to check in our website and register if you want to receive this information and this kit. Now, what we are here today to talk is about the webinar titled Simulating 2D Hydrodynamics at 30-meter resolution for the entire planet. For this, we're very honored to have Professor Paul Bates. Paul Bates is a professor of hydrology at the University of Bristol, and he is also the chair of the flood risk analytics firm Fathom. He has worked around all the topics of shallow water equation combining with satellite and airborne data to understand all the flood dynamics, all towards reducing threats to life and the economic losses worldwide. Paul has worked with different researchers around the world, with NGOs and multinational companies, also in the insurance industry, to manage flood hazard and risk. He's a fellow of the Royal Society of London and the American Geophysical Union. He's a double winner of the Lloyd's of London Science of Risk Prize. And in 2019, he was made commander of the British Empire for the service to flood risk management. He was recently awarded with the John Dalton Medal by the European Union of Geoscience in 2024, and more recently, the Bente Chao Award by the American Society of Civil Engineers in 2025. So thank you very much, Paul, for accepting and for delivering this webinar. We are really honored to have you, and without further ado, the floor is yours. Thank you.
Well, thank you, everyone. And firstly, thank you very much to Rafael and mostly to Dina for inviting me to speak to you all today, and to everybody for coming along. I'm honored and very, very grateful. It's a great turnout. Let me just share my screen and we will get going on the presentation. So allow me to just... So hopefully everybody can see this.
All good.
Let me just get rid of the meeting controls. Okay, so I understand from Dina that in large part, the community I'm talking to today come from the earthquake and geotechnical side of hazards, and maybe floods and hydrology is slightly new. So do, if I go too fast on anything, do put a question in the Q&A box, and we'll come back and try and explain that afterwards. But as Rafael kindly said, my work revolves about solving the shallow water equations, which allows us to simulate the movement of water over a complex topography. In other words, I simulate floods. And after starting my PhD building models of river reaches a few tens of kilometers in length, over time, we've developed the data sets, the numerical tools, and the high-performance computing to allow us to extend those methods to cover the entire planet at a really extremely high resolution, 30 meters, in fact. If you think about global climate models, which typically operate with horizontal resolutions of 50 to 100 kilometers, this is an incredibly granular view of the Earth's surface. And the reason why we do that is that all flooding is local. So if we look at the hazard maps or hazard footprint of a flood event, the difference between being completely safe and being a property being totally destroyed can be of the order of a few tens of meters. And therefore, we need our models to be that granular in order to be able to pick out these very fine, granular patterns of hazard and risk. This would, of course, be very different for earthquakes, for example, where the footprints are relatively, I mean, a much smoother in space than that. And therefore, some of the data requirements here are really extreme, and some of the computing requirements as a consequence. Anyway, that's to start off by saying that in looking at flooding, we're in a subtly different part of the hazard mapping spectrum, and that leads us to some different choices. And clearly, this is such a big undertaking, you can't do all this on your own. So I need to thank a very large team of people who've helped over the last decade to do this, only some of whom are shown here. And this work has been delivered both in my research team at the University of Bristol and also with a company that I and some PhD students founded in 2013 called Fathom. And we came to the conclusion that actually to build the research team that we needed to deliver flood inundation modeling over the whole planet, we couldn't really rely on grant funding from governments. There's no way I could go to the UK government and say, okay, I need a team of 30 postdocs for 10 years, and I'm going to need £500,000 for computing. They'd just laugh. So instead, what we've done is leverage commercial money to build the team that we think we need to do this. And that means that we develop commercial products, but we also make them available for academic research. So let's look at flood modeling then. And it's probably, if you're in the geotechnic space or quake, you've probably not thought about this too much, but over the last 10 years, global flood models have been a rapidly emerging paradigm. Prior to this, we used to build models over river reaches a few tens of kilometers in length. And if we wanted to map an entire country or an entire region, we would build multiple instances of a numerical model. Different research teams, governments would commission research teams or consulting engineers to build models of individual tens of kilometer river reaches. And then over time, those would be stitched together to produce the national map. The problem with that is it's very expensive, it's very slow, and you can't easily re-simulate if you think, I want to simulate some different climate scenarios, or what happens if the population changes or the land subsides. Just to give an example, in the US, the National Flood Mapping Program got going in 1967. And as of a couple of years ago, the American Society of Civil Engineers estimated that around about $10 billion had been spent on those mapping programs and individual modeling studies. And yet less than 33% of the rivers in the US had been covered by that point. And most of the models were more than 10 years out of date. So against that background, during the 2010s, people started to think about the idea of taking the numerical modeling techniques we had, but applying them at scale using data sets that were increasingly available for the whole planet. And just for the flood models that we developed, here are how they've evolved very rapidly over the period 2015. So at the top, you see our version 1 model. This operated at 1 kilometer native resolution, and it's detailed in this paper by Sampson et al. And when we saw this, and we thought we were so clever, we thought this was, to be able to do this was brilliant. And hey, look, these floods, we've got a simulation. But over time, looking at this in hindsight, and it's not that great. The flood appears and disappears along the river corridors. Lots of the tributary valleys don't have any flood risk in them. The results are very smooth and kind of blobby, and intuitively now they don't look particularly realistic. And over time, we've developed these models, both the techniques used, but also the data sets. And one of the principal things that has changed has been the quality and resolution of the terrain data that's gone in and the compute power that we can deploy to simulate it. So by 2020, we were simulating at 90-meter native resolution using new global digital elevation data. And the DEM data is the key source. And then, so by 2020, this is looking a lot better. We're picking up flooding along the tributary valleys, but nevertheless, everything, the flooding looks a bit extensive. The DEM is probably too smooth, and there's no real detail in here. And fast forward through to 2024 and version 3 of our model, and now this is starting to look nice, really realistic. You can start to see floodplain geomorphology in the terrain data, and we're correctly getting confined flooding along the narrow river valleys. And we've got ideas in place for versions 4, 5, and even 6 of these models. So there's more developments yet to come. So how do you do that? Well, I mean, it's quite complex. These models are now, they're a similar complexity to a global climate model. It's the best way to describe them. So if you are a hydraulic modeler and you are used to building standard models like HECRAS or TwoFlow, those are schemes that are quite complex, but a global climate model pulls in an awful lot of data and does a lot of model building as well. But having said that, what we're doing here is essentially replicating and automating the steps that a practicing hydraulic engineer would take to build a hydraulic model of a particular place. So if you're a hydraulic engineer and somebody said, build me a model for this around this town and work out the impact of building some flood defenses, you would get a numerical model, you would take some terrain data, you would take some observations of river flows and rainfalls, and you would pull all that together. And so when we're doing this globally, all we're doing is, instead of a trained person doing that, we're encoding those operations in a bit of computer code that we call the model builder, and then pulling in data sets automatically building numerical models for sections of river over the entire planet, solving those, and then post-processing and producing the flood hazards. So if you can see in box 2, right at the heart this is a classical hydraulic modeling problem. You have some model code which solves some physics-based equations that simulate how water moves over the landscape. You might need some terrain data to go into that and some details of the river network. Because we don't know the river bathymetry globally, we need to actually, first of all, estimate that, which happens in the channel solver. But then that's a classical hydraulic modeling setup. And it needs driving with boundary conditions. It needs driving with boundary conditions, which come here in box 1. This is taking tide gauges, rain gauges, and river gauges, running them into statistical models called regional frequency analyses, and producing estimates of the magnitude of extreme flows and rainfalls or coastal water levels across the entire planet for every river or every grid cell. You might increment those frequency estimates into the future by looking at the climate change signal in global climate models, and that's what happens here in box 3. And then in box 4, there's some post-processing that we do. We add in the flood defenses because those are critical to whether areas inundate or not. And we also have this thing called the interpolator, which we can take a limited set of climate simulations and interpolate to other scenarios which we've yet to simulate. So we simulate all levels of global warming up to more than 5 degrees above pre-industrial. And we can use that to recreate any particular set of climate scenarios that we want. So it's complex, but it's just classical hydraulic modeling scaled up and automated for the planet. And what you're doing is this. This is a 2-dimensional simulation of flooding it happens to be a river reach in the UK, over a few tens of kilometers from top to bottom here. And we are building automatically hundreds of thousands of such models tessellated together over the entire global river network, simulating those, and then gathering all the results back and joining those together in geographical information systems to make the final map. And so, yeah, very pretty. And this looks, passes a sniff test. Looks like a real flood, compares well to observations, but we'll come on to more of that later. So there's a number of things that we need to make that work globally. We've known for a long time how to do that for individual places, but there are some tricks, better ways that you need to work in order to be able to do that in a global way. And the first of those is you need the right model structure, because as I said, there are no global data sets on river bathymetry, so the depth of rivers. Neither are there any satellite data sets that will either available or planned that allow us to estimate that. And therefore, you need to instead treat the river depths as a further parameter in the modeling that you need to estimate. And if you do that, a 1D, 2D structure is ideal. This also allows you to decouple the width of the river channel from the grid dimensions. Clearly, if you want to simulate the river channel with a fully two-dimensional model, you need a very small grid size in order to be able to map the complex terrain of the river channel and then have these large flat areas on the floodplain. So 1D, 2D models help with interface well with the kinds of data that we can get globally, and also allow us to represent any width of river channel, irrespective of the resolution of the overlying grid. Our best global DEM is 30-meter resolution, but often we want to represent river channels that are much smaller than that. Many rivers around the globe are smaller than 90 meters, and if you've only got a 30-meter channel, you can't really represent their geometry at all. So a 1D model structure is important. Second thing that you need is that the numerical scheme that you're going to solve needs to be really quick. I mean, 30-meter resolution over the entire planet, and that's around about 130 million square kilometers. It's round about 1 billion computational cells, and you need to run dynamical simulations of a physics-based model over all of that for multiple return period events. Even with 2,500 cores, which is the size of our compute facility, it takes many months to do a whole global simulation just for one particular case. And that's even with a really fast numerical model. So this is the one we use. It's called ListFlood FP. It solves the local inertial form of the shallow water equations. I'm not going to go into the maths, but basically what it's doing, it's moving blobs of water around on a grid according to laws of mass and momentum conservation. That's typical of all hydraulic models, but the key thing here is that this lower equation, which calculates the flux from one cell to the next, is really cheap to solve on a computer. Numerically, it's an explicit finite difference form of the equations, and therefore it's very cheap for that reason. And it's only got one power expansion term here, this h flow to the power of 10 over 3 in the denominator of the equation. Power terms are expensive to do even on modern computers, and that's the only thing that causes any cost. So this is, as far as I know, about the quickest way to derive a shallow water equation is with this numerical scheme. Even then, you need to deploy high-performance computing. You'll need to have software engineers work on the code to improve its performance. And for example, in this paper here, Jeff Neal and Toby Dunn, who is a trained software engineer, looked at our code and without changing any of the physics, achieved a 10 times speed up just by reorganizing what was going on. You will wait a long time before Intel delivers you a computer chip that is 10 times faster than the one that you've got at the moment. You're going to need an automation framework because clearly you're not going to be able to model each individual reach as a bespoke practice and do that individually. So you need to automate all the things that a trained engineer would normally do. And then you're going to need some really key data sets. And for flooding, the most important thing that we can provide is the digital elevation model. And here what we really need is the bare earth digital elevation model, which you could also call the digital terrain model, or DTM. And that's because water does not flow over the top of trees or over the top of buildings. It flows underneath or around them. So most of our global digital elevation data come from radar satellites, which are capture the tops of objects. And therefore we need, using rather fancy machine learning approaches now, identify those objects and strip them off and deal with the errors in the global terrain. Fortunately, I've worked over time with some really clever people who are great at doing this. And so just an example, this is one of the global terrain data sets that has been in use for now quite a while. It's the Shuttle Radar Topography Mission data, which was collected in 2000. And this is it over the Mekong Delta. And you can see here these strange parallel lines in the data. And these are satellite long wavelength errors as the space shuttle slowly pitched and yawed as it flew across the region. And you can also see on here that there's vegetation and buildings and just noise and speckle as well. Unfortunately, this is the cleaned up version after correction. And this is the work of Dai Yamazaki and to produce the Merit DEM back in 2017. Since Merit, actually, my colleague Lawrence Hawker has been spending some time producing a even higher resolution, which we called FabDem, that we've used more recently. And this comes, instead of now shuttle radar topography, this now comes from the Copernicus DEM. But again, same problem. The data sets the satellite agencies put out are surface models, capture the include surface artifacts, and those need to be stripped off and corrected. Once you know the DEM, you also need to know where the rivers are. And again, clever people over the last decade have addressed that problem also. Dai Yamazaki, again, with the Merit Hydro dataset, and George Allen and Tamlin Pavelski have both provided these wonderful datasets which show the global river hydrography, so where rivers are and sometimes what their widths are as well. So we can get location and width of river, but there's nothing that will tell us the river's depth. And I'll come to that in a bit. We need boundary conditions, most obviously. We need extreme flow and rainfall and coastal water level everywhere. And here, what we do is old school hydrology that we've known about for 50 to 60 years now. And these are the regionalized flood frequency analysis methods that most national governments have for estimating flows in ungauged catchments. The difference here is that we've been able to apply these models globally using newly available global catchment characteristics data sets like the vegetation cover, urban areas, land use, slope, rainfall, and so on. So here's some work by PhD student Gang Zhao using machine learning to estimate design flood magnitudes based on catchment characteristics. So we take the set of global flow measurements that we have, and we use random forest regression and other ML techniques to be able to extrapolate to places where we don't have river gauge information. These curves vary by climate, and as you can see, this is observed versus simulated estimates of the 1 in 100 year return period discharge in different climate types. And we get a mean bias here of less than 20% for all flood magnitudes. And that's really important because actually you can probably not measure global discharge in rivers to less than 10%, even in good conditions. In flood flow conditions, if you can measure discharge to less than 20%, fantastic. Most of the time you cannot. So once these relationships get less than a 20% bias, you're within the error of the observed data. As I've said a couple of times, we don't have global river bathymetry, and therefore we have to estimate that. in some way. And the way we do here, this is a method developed by my colleague Jeff Neal. And we use gradually varied flow theory to invert where the bathymetry should be, given an estimate of the height of the channel banks, which we get from the DEM, and an estimate of the bankful discharge, which we get from our regionalized frequency analysis. So it's a common law in hydrology and geomorphology that self-formed alluvial channels, the return period of bankful discharge, so the incipient when it's about to start flooding, the return period of that flow in a self-formed channel is usually around about 1 in 2 year return period. So if we take the 1 in 2 year return period from our regional flood frequency analyses and the top of the channel banks and the channel slope, we can use the gradually varied flow theory and a nonlinear optimizer to invert where the riverbed should be to create that water surface profile with that discharge. Now, this is really important for getting this to work globally, because what we've done here quite quickly is we've collapsed two uncertain variables into one. We don't know the depth of the channel, and the depth of the channel is uncertain, and the river discharge, bankful discharge, is uncertain. If we estimate both of those independently, it's very easy to get a mismatch. You can either have the channels too big for the discharge or too small. If you collapse those and tie those together, you might be wrong, but you're always wrong in the same direction. So this is a way of almost bias correcting two uncertain variables and giving us something that's much more easy to estimate. This really is the secret to making this work globally. Otherwise, it's very difficult to do. Yeah, I'll skip over. We need some flood protection standards. And here, Scuzzolini et al. Have produced this database called FlowPros, which tells us, at least at country or sub-country level, what the flood protection standard is. And we can actually, instead of the bankful standard geomorphology assumptions, we can, if we know a channel, if we know a location is protected to, say, the 1 in 50 year return period, we simply can use that in our bathymetry inversion and say, okay, well, now make the channel such that it could hold the 50-year return period flow, not the 2-year return period. So we can use this in our channel flow solver. And then to do the climate change analysis, we need some climate change projections. So here what we're using are the CMIP5 and different CMIP5 and CMIP6 ensembles. And so for pluvial, we use a high resolution climate model ensemble because that captures rainfall better. For coastal, we use the IPCC AR6 relative sea level projections. And for changes in fluvial flows, we use this CMIP5 archive using the ISIMIP2B global hydrology model ensemble. And what you can see is that there's a distinct geography to climate impacts for flood. And that geography varies depending on what kind of flood driver we're thinking about. In these plots, green is an increase into the future and brown is a decrease. And we're looking at particular extreme flood quantities here. So you can see that rainfall increases everywhere, more or less. It increases most in areas where it's low now, but it increases more or less most parts around the world, apart from some bits of South West Africa, bits through the Amazon, according to this ensemble. The hatching, which on these plots, which you might not be able to see, shows where the models actually disagree on the sign of change. So here we're quite uncertain. Sea level increases pretty much everywhere. That's fairly well locked in, even with current emissions. The only place that changes is close to the poles because of glacial effects and the weight of ice there. For flooding, we've got a really mixed signal. Not only do the models more often disagree on the sign of change, there's lots of parts of the globe where actually peak flood flows in the CMIP5 runs look like they will go down. Southern Europe, Eastern Russia, North Africa, Middle East, Australia, Southern Africa, quite large parts of the US are all places where we think according to this climate model ensemble, flood flows will go down. Of course, if you had a different climate model, you might have a different set of projections, and we could take that into account. But these are the ones, these at the time we did this modeling, these were the best ones we could use. So here's the detail. I won't dwell on this. Let's skip over. I've told you enough about this stuff already. What does it look like? More importantly, here's Houston, and this is the area at risk from a 1 in 100-year coastal flood in 2020. And you can see the kind of granularity we've got, largely driven by really, really cool digital elevation data is the key thing that makes this look quite so good. And this is the additional flooding that we forecast given those sets of data by 2050 as a result of changes in mostly sea level here and some changes in storminess. Okay, so the model works, it looks great, but the question you should all ask is, fine, yeah, Paul, is it any good? How well would it predict a flood that you might have observed in the past? And we've tried to test that in a number of ways. Firstly, we've compared the model to national and regional engineering hazard maps, both in the US and the UK. And these are the national mapping programs where trained engineers build models of particular places. Those are built up as a patchwork and are stitched together to produce a national map. You would assume national mapping, that kind of locally done, expert-driven mapping modeling would be better than a global automated method. So we can use that as a validation source. We can use satellite images of floods, which we have a few. That works okay. And satellite remote sensing of floods is not perfect. There are errors in that. And actually there are errors in local models as well. But all the time we're comparing non-error-free models to non-error-free data. And we've got some post-event reconstructions of maximum flood extent we can use. And we compare them all together using this metric called CSI, or Critical Success Index. And this is basically the intersection over union of this 4-part contingency table. So it's the area that we correctly predict as wet in the model, the intersection of the model and observations, or area D, divided by the total area of the correctly predicted, the under and over prediction. So you can think of this as the functional floodplain. It's anywhere that either the model or the observations thinks is flooded by in a river flood. We ignore the large area A where the model is dry and the observations say it's dry. And the reason we do that is that usually floods are small and model domains are big. So if you take into account area A, you bias your results quite significantly. It's quite easy to get area A right. In fact, most of the time, the flood's only about 15% of the total model area. Therefore, if one said, actually, there's no water in this domain at all, you'd probably get an 85% prediction success rate, which would not really convey the skill of the model. And then lastly, we've got a bunch of situations where we've measured high water marks, and there we can test that with a mean absolute error. And this is what this looks like for a whole set of these test cases. We've got 3 diagrams here. If I take panel A first, this is the critical success index, so the area matching metric for each of the cross or a circle is a different test case, and we've classified them according to their return period. The crosses are for our version 2 model, and the open circles are for our version 3. You'd obviously want to be getting better over time. So we want the circles, critical success goes from 0 where there's no overlap to 1 where there is a perfect match. So we want these numbers to get larger we want the circles to plot above the crosses. And by and large, they do. Where our models were already good, the improvement is sometimes marginal, but always there. And in places where our version 2 model was pretty bad, actually, we get quite large improvements as well. So that's all good. We're going in the right direction. In panel B, we've seen the same thing, but now this is the watermark data. And this is mean absolute errors, and we want these to go down. We want the circles to plot underneath the crosses. And in panel C, we see the error histogram of these water level errors. And clearly we want that to between version 2 and 3, we want that to sharpen. We want the histogram to sharpen and to center more on the 0 water level error. And clearly we do that as well. So to summarize these statistics, across all these tests, the CSI is improving up to 0.75, and the root mean square error is going from 1.9 meters down to 0.69. Let's put that in context. If I were to build a fairly standard local model, I've built a few models in my time. If I built a model of a particular site and I compared it to a satellite image, if I got a CSI above 0.8 or 0.7, above 0.7 I'd be happy, and above 0.8 I think I'd be doing really well. The best I've ever done is a CSI of 0.9. And that's because the model's got error, sure, but the satellite data has error as well. And you get to a point where actually you're within the error of the observed data. And we're approaching that here. Root mean square error, the best I've done in a local model is around about 30 centimeters, comparing to watermarks that you measure after an event. You go out after an event, you measure watermarks on walls and trash lines. Actually, those aren't perfectly aligned with peak flow, peak water level, and so they tend to have errors of a few tens of centimeters. So if you can get a model to about 30 centimeters, that's as well as can be done. Here we're getting to 0.7 meters, so there's a little bit of improvement here. But when I tell you that the DEM, the base DEM error, is about plus or minus a meter, this root mean square error is within our DEM vertical error. And again, it's very difficult with DEM data of that sort to do much better than this. And so we can use these models to project estimates of global flood hazard and with their uncertainty into the future. And here's just an example from our paper. And this is the change in global flood hazard out to the end of century under 2 climate scenarios, SSP1 and SSP5. SSP1 is tantamount to, this is a climate scenario which follows the Paris Agreement targets. We peak global carbon emissions peak mid-century and thereafter decline. And this is the kind of net zero climate stabilization scenarios envisaged under the Paris Agreement. SSP5 is a climate where global warming above pre-industrial levels probably exceeds 3 degrees. Climate turns out to be a bit more sensitive than we currently think. So you could think of these as bracketing the best case and the worst case normal scenarios. And what you can see is that, if we hit the Paris Agreement targets, flood hazard increase peaks about mid-century and thereafter increases slowly, but within manageable levels. SSP5, on the other hand, flood hazards are still increasing strongly out to end century. There's quite a degree of uncertainty over these because of the spread of climate models that we're using. The shading represents just the one standard deviation uncertainty from the climate models. And you can see that there's differences in the trajectories and uncertainties depending on whether you're looking at pluvial, fluvial, or coastal modeling. Coastal, we're most certain about. Sea level rise is more or less locked in. Fluvial flooding, as I've said, the climate models really do disagree often on the sign of the change and the magnitude. But to summarize, SSP1, if we hit the Paris Agreement targets, median change by end century is about 10%. That's within our uncertainty in characterizing that in the current climate. And I think we'd say that 10% we could probably, hopefully, as a planet, engineer our way through. Increases of 50% by end of century is much more problematic. And that starts to ask some very serious questions about flood adaptation. Of course, what I should say is that these are headline global figures and they will conceal very strong changes in the geography of risk. So some places, even under the best case scenario, will see large, strong increases in flood hazard, and other places might actually see strong decreases as well. If those projections of fluvial flood hazard turn out to have any truth to them at all, fluvial flood hazards could go down quite markedly in large parts of the world, even when rainfalls are becoming more intense. And that's because even though rainfall is more intense, some of the time it falls on drier soils because the inter-rainfall periods are probably warmer and evapotranspiration during those periods is higher. So the last thing I'm going to talk about is the idea of maps versus models. So what I've shown you so far are ways to produce maps. And you can think of these as showing you what gets wet where. But what they don't tell you is what gets wet at the same time. Those maps are just, this is the area that would be inundated if the 1 in 100-year event were to happen everywhere globally simultaneously. And obviously that's completely unrealistic. That's not going to happen. Instead, events hit particular places. And even in those places, the intensity has a footprint, just in the same way that the earthquake hazards, an earthquake would have a footprint. The intensity would be high near the epicenter and would decrease the further away that you got. Same thing with floods. Bit more spatially complex because of the landscape, but same basic idea. Maps are static. They produce at the depth for a given return period, and they allow us to look at individual locations and visualizations. Often what we want to do when we're thinking about risk, and particularly risks for the insurance sector, is to look at spatially correlated financial losses. So what's the worst loss that a particular country or company could experience in a given year for a given territory? And here we have to do something slightly different. Here we need to simulate large numbers of synthetic events. And that's because we need these realistic spatial patterns of intensity within our events in order to look at anything more than average annual losses. And these are the things that we developed for the insurance industry for quantifying losses to portfolios, but you could also use them for national governments as well. You know, how many, what kind of resources do you need to deploy? You know, what's the worst flood that can happen simultaneously in a country? So where, what's your worst case scenario? So how do you go from hazard to risk? And the way that you do that is this branch of science that the insurance industry has developed over time called catastrophe modeling. The first thing these need are a set of the spatial extent of events and also how the intensity of the event varies within that spatial footprint. We develop these by complex statistical analyses looking at the cross-correlation across a set of measurement locations. Once you've got those, you can then define the hazard within that footprint. So you can look at the return period of the hazard in a particular cell, extract from our hazard maps the corresponding set of water depth predictions that we get in that territory, and cookie cutter all those together to produce a flood depth map for the event. Then we need to build in our loss metrics. Firstly, we need something to do with exposure. And this is the same if you're, same data sets if we're dealing with quake or with flood or any hazard. We need to know global asset distributions. We need to have really fine, in our case, we need really fine granular data on what these are. We need to know this down to individual building level on a planetary basis. Then we need vulnerability curves. We need to know if a flood event of that depth were to happen, how would the structure that exists at that location be affected? So we need depth damage vulnerability curves for each asset class and how those might vary across the globe. And then lastly, for the insurers, we might need some financial module at the end, which these are think of these as the terms and conditions on your house insurance, when financial institutions are reinsuring, issuing reinsurance contracts, they will have these layers in them which say, okay, well, we're not going to pay anything up until we get to $100 million of loss, and that kind of thing. So this is what CAT models would do. We would stochastically generate these sets of events that would be happening all over a particular territory. We'd define the spatial intensity footprint for that, and then the depths, and then the exposure and the loss. And we'd be able to summarize those over time to quantify financial risks, to understand risk accumulations, and to say something about particular portfolios of assets. Let's have a look at how, just to finish off the seminar, how those might work. So these are, there's a number of ways that we've made these risk estimates in the UK. We've got some national flood risk assessments, which our environment agencies have done. We've got a UK-wide climate change risk assessment, which builds off the national flood risk things. And we have some insurance industry catastrophe risk models. The problem with all of those is there's limited or no method information about how those were done. And there's limited or no validation, and they're not peer reviewed. But one thing we know is that they don't match observed losses. So we have observed losses over the last 20 years from the Association of British Insurers. And if we put all these on an identical basis, we can see that the National Flood Risk Assessment and the Climate Change Risk Assessment are about 3 times higher than the observed losses. They're saying annual average damages of over 2 billion, whereas the observations say about 700 million. So to examine that conundrum, we built a similar hydrodynamic hazard model for the UK, but we also did this catastrophe modelling step that I've just been talking about. So the catastrophe modelling step appears here in this box. Hopefully you can see my cursor. We're doing this, we're creating sets of many tens of thousands of years of realistic flood patterns and estimating the losses for all of those. So here's the data going in, here's the standard hazard modelling, here's the climate projections, and here's the catastrophe modelling. And you can see we've got this UK buildings data set going into the exposure data. And for the vulnerability curves in the UK, we have, for flood, we've got this thing called the multicoloured manual, which gives commonly accepted vulnerability curves for different types of assets. And out at the end, we get the risk metrics. It looks very similar to the modelling I've just shown you. It's applied at 1 arc-second resolution, so that's 20-25 meters at this latitude. All the flooding types, built with better terrain data than the global model. This is from LiDAR. Lots of return periods simulated. Flood defences we know about in the UK quite nicely. We simulate 10,000 years of stochastic flood events. We have the Met Office here to produce climate change projections. And then we take all these analyses and we compute the monetary losses for 5 specific global warming levels. So we're going to come up with something called a loss exceedance curve for particular levels of global warming. But first of all, let's have a look at the financial validation. So here in this graph, we show the observed Association of British Insurers expected annual damage of 700 million. This is the vertical line just here. And the other 2 vertical lines are the ones from our national risk assessments. From the stochastic model, this histogram in green, we've taken 10,000 random 20-year periods from the 10,000 years of flood model simulations that we've done. And we've calculated the expected annual damage for each of those 10,000 20-year periods and produced a histogram of those. So you can think of this histogram as reflecting climatological variability in flood losses. Obviously, over time, you can, by chance, get 20-year periods which are flood poor or 20-year periods which are flood rich. Taking that stochastic variability into account, this is how you would estimate your expected annual damage would vary. So in a given 20-year period, just by climatological variability, our EAD could be as high as 1.5 billion or as low as 400 million. But the median sits very close to the observations, without any calibration. So that's pleasing. Our observed history, our model histogram brackets the observations. It also shows what we suspected, that the national analyses lie well outside any climatologically realistic loss distribution. And this is what we get then. We have some trust in these results. So this is what it tells us about UK flood losses under climate change. These are loss exceedance curves. You'll get the same thing for quake in the insurance field as well. And this shows the probability exceedance of different losses. So the probability is in years and the loss is in billions of pounds sterling. So 10 to the 2 is 1 in 100 years. And this says that under current and with 0.6 degrees of global warming since pre-industrial, once every 100 years, we can expect the UK annual flood loss to exceed round about 4.8 billion pounds. So once in a century for 2020 climate, we might, for a climate with 0.6 degrees of global warming, we might expect the total annual UK flood losses to exceed that amount. Once every 10 years, they might exceed 1.67 billion, something like that. And we have these for different global warming levels. So 1990, this is round about, this is where we have 0.6 of degree of warming above pre-industrial. And that's where we were then. By the time we get to 2020, so just a few years ago, now we're at around about 1.1, 1.2 degrees of warming above pre-industrial. And actually, these curves have not changed a great deal. They're probably within experimental error here, or numerical model error. That's pretty much true all the way out to 1.8 degrees of warming. This is where the climate might get to if we meet all the COP26 pledges and also the net zero ambitions that countries have put forward. So if we do everything in the Paris Agreement plan and more, we stabilize global warming since pre-industrial at 1.8 degrees. UK changes in UK flood loss exceedance curves are pretty moderate and again, probably manageable with sound engineering. If we don't meet those net zero targets, if we just do the COP26 pledges, we'll probably get to about 2.5 degrees of warming above pre-industrial. This is about current trajectory we're on, maybe slightly higher, 2.7, 2.8. Here then, we're starting to see quite substantial uplifts in the loss exceedance curves. And if we get to 3.3 degrees of warming, this is climate targets missed, climate more sensitive than we think it is, then we might get losses, 100-year flood losses might be 40% higher than they were in 1990. This table just puts that into account. You can see where we get, 3.3 degrees is our plausible worst case. Expected annual damages in the plausible worst case might be 23% higher than 1990, nearly 40% higher for the 100-year losses. The losses are much less clearly as you go down. If we meet the Paris Agreement targets and you hit 1.8 degrees, actually the change in the 100-year loss is less than 10%, we think, and therefore much easier to cope with. But like I said about global, these national figures conceal large variations in the geography of risk. So on the left-hand side, this is the historical expected annual damage in thousands of pounds for 10-kilometre hexagons across the UK. And you can see that the values are high where the population is, in London, in South Wales, in the conurbations of the Northwest and the Scottish Central Belt. On the right-hand side, this is the percentage change in expected annual damage with 1.8 degrees of warming. Now, remember here, the EAD at a national level is only increasing by 4%. But look at the geography. In lots of places, actually, the expected annual damage goes down with 1.8 degrees of warming. There's a large belt from southwest England through to northwest England and northeastern England, northeastern Scotland, where actually losses stay about the same or maybe even go down a little bit. But there are other parts of the country, Western Wales, especially South Wales, the very populous southeast of England, bits of the northwest and the Scottish borders, where losses go up really quite strongly. So greater than 25% increases, even if we hold carbon emissions to a high target. So to conclude here, we can now model global and regional flood hazards really quite unprecedented spatial resolution and accuracy. Outputs compare well to observations, even with quite comprehensive and detailed analysis. Our skill approaches local models and also the error in the observations. We're wringing quite a lot out of these data. For future flooding, the climate pathway really matters. And these headline figures conceal large changes in the geography of risk. Some places losses go down, others will face much greater than average increases. And those were some spare slides I had, but with that, I've come to the end. So thank you very much for listening, and I'm very happy to take any questions.
Thank you very much, Paul, for this very comprehensive and very easy to follow talk at the same time. I believe that we have learned quite a lot about flood modeling at large scale, and what are the consequences of floods. Before we open the mics to questions that we have received online, I just would like you to reflect just a moment on what is the importance of having the ability to model at global level, as you have done with this model.
Yeah, so I think that's a really good question. For a lot of the time in hydrology, we think about local places. We're designing a reservoir or a flood defense for a particular place. And particularly in flood hazard management, that's how we've classically thought. But there is a whole tranche of flood risk management questions which occur at much larger scales. So, for example, how much should a country spend on flood defences? So if you're going to your national treasury and trying to put forward an economic case for investment in flood defences, these are the kinds of data that you would use in order to develop that case, because they tell you what the expected annual damage might be, and they could also be used to tell you how much you could mitigate those with particular amounts of spend on flood defences, really quite easily. Similarly, if you're an insurer, your losses are mutualised at the scale of whole countries. That means when the regulator comes to you and asks you to prove that you have enough capital available to pay out your losses if a really extreme year were to happen, they will ask you to be able to say, they will want you to be able to demonstrate an analysis that shows the magnitude of the 1 in 200 year return period loss to your portfolio. And they'll want you to demonstrate you have capital available in order to do that. Similarly, if you are, say you are an infrastructure developer, you're a company who develops solar farms all around the world, you will have a need to know when you're developing sites whether they're at risk of flooding or not, because if they're at risk of flooding, you could lose your investment. And similarly, if you're a very large investment firm, you might have portfolios of assets and properties, and you will want to know, okay, these could be located anywhere on the planet, and you would want to be able to calculate how at risk are these from flooding, both now and in the future under particular climates. particularly if they are really long-term investments like ports or oil refineries or nuclear power stations, for example. So anywhere where you have national or to global scale decisions or portfolios to evaluate, these models really start to come into their own. They're the only way that you can address those problems.
Thank you very much for the answers. And I just wonder whether you could give us a sense of how physically correlated event can be on a global scale, and therefore when you then start to zoom in on defining a particular level of hazard or risk, what is the best scale to think about, considering the global weather models and the global weather forecasts?
Okay, so flood risk we know is really granular. So you always need these ultra detailed views of hazard and exposure and vulnerability. It's an inevitable consequence of the quite small scale variations in hazard that you get. You know, the difference between being completely flooded and being above the flood level and dry could be a few tens of meters. You know, from disaster to safety can be a very, very small distance. But then, you know, when we take that out a little bit, you know, we have actually, Dina, what was the second part of your question? Let me just get
what is the best scale depending? What is the correlation between events, and therefore what is the best scale at which considering a particular level of risk or hazards and therefore risk?
So that's okay. So we always have to have this underlying granular view, but events can be correlated. I mean, they're correlated within the footprint of a given event. If you think about a tropical cyclone hitting a country, it will impact a swathe of a country as it travels across it. So you might expect correlated hazards anywhere within that affected track, which might be hundreds of kilometers across. So I think correlations in flood hazard, you know, you see over a few hundreds of kilometers. So if you do an analysis of gauge data and look for, say, what's the correlation? If gauge X is in flood, what's the probability that other gauges are also in flood at the same time? You find that the distance decay is a few hundreds of kilometers away from the peak intensity. Nevertheless, you can get flood events happening simultaneously, but in very different parts of the globe, but driven by different flood drivers. You can have floods in Indonesia and floods in Brazil at the same time. Some of that is chance, but also that we know that there are some large-scale climatic drivers, for example, El Nino Southern Oscillation and others, which can lead to teleconnections between places. And you might find that, for example, with El Nino, I think it's La Nina years, it leads to increased incidences of tropical cyclones on the eastern coast of Australia, along in Queensland. So you get these large-scale teleconnections which change the probability of experiencing events. And you might find some places the risk is anti-correlated, which is an important part of developing insurance portfolios.
Thank you very much for the answers. Again, very comprehensive. So I think we have quite a number of questions. I also see that Rafael has raised his hands. I don't know if you want to communicate something.
Yes, Dina, I just want to do a follow-up question of the discussion, if that's okay. So yeah, first of all, Paul, thank you very much for the presentation. The model that you have developed is quite interesting, and the applications are huge. It's very impressive to see how you first develop the FATDEM and then go until the quantification of economic losses and how all this is connected. My question is following up what Dina's discussion, and if you are in the shoes of a decision maker and a government, for instance, you will have, for instance, all these models. You will have modelings for different years, for 2030, 2050, 2080, and you have four different shared socioeconomic pathways. One in agreement with the Paris Agreement, and the other like the worst case scenarios. From your experience, what would you recommend to the decision maker? Like going to the most extreme case, to the most optimistic, the middle one, develop different analysis, and based on that, make the decision. Like what has been your experience in that sense?
So there's quite a lot of interesting work that has looked at adaptation decision pathways, and when you need to take particular decisions, and when particular decisions should be triggered. So, for example, flood defenses can take many decades to develop, and therefore, if one needs those defenses in place by a particular time, actually you need to take that decision a long way ahead. So there's all this nice work on adaptation pathways. But my recommendation is that I think you need to simulate a range of climate scenarios. You need to think about the uncertainty in those. For coastal regions, you need to think about what happens beyond 2100. One thing we know about sea level rise is it doesn't stop in 2100 and stabilize. Sea level will be continuing to rise out to 2300 and beyond. So you might want to think about whether your decisions are robust to potential changes that might be actually in the quite far future for certain types of activity or categories of asset. So yeah, I would consider a range of scenarios plus uncertainty, and I would think about the sensitivity of the decisions you're making to getting the, which pathway that you're on.
Thanks. We have a question from Abdul Wahid. I don't know if we can open the mic for Abdul, Rafa, or the question is about the relevance of temperature as an important variable to climate, of course.
To an extent, yes. I mean, insofar as the Clausius-Clapeyron relationship dictates that increasing temperature means atmospheres can hold more water, clearly temperature is a really important variable in the climate system, and it's intimately connected to the water cycle. It also influences the amount of evapotranspiration we will get into the future. And so it comes back to this point I made, that even though in warmer atmospheres can hold more water, we expect an intensification of the hydrological cycle. So we expect more frequent and more intense downpours. It may be that the inter-rain periods are drier, and therefore when rain falls, in some places it falls on drier ground, and therefore it doesn't generate the non-linear runoff response that you might expect. So I think temperature is important because it points to the non-linear relationship between rainfall and runoff. And many climatologists confuse rainfall with flooding. Those are not the same thing. Neither is rainfall, neither is river flow flooding. There's a linear transform from rainfall to river flow and from river flow to flooding. And you need both of those non-linear transforms in order to get to the risk.
Thank you. There is a question from Abbas Fatih Hazar. Maybe we can open Abbas' mic, and can you introduce yourself and ask your question?
Yeah, thank you. I'm working on multi-hazard risk. I have some idea about earthquake. I was wondering how, in which part and how this spatial correlation factors into hazard and then into the risk assessment. Because in earthquake part, we somehow force the intra-event residuals to follow a multivariate, spatially correlated distribution. But could you please elaborate how and where in the flood part it enters into the equation?
So thanks very much, Abbas, for the question. Did I understand correctly? You were asking about the correlation, a multi-hazard being earthquake and flood, and whether how that correlation was taken into account, or was it something specific, something else that you wanted?
No, I just want to know in the flood part, I mean, mainly in flood hazard, because then it can be translated into risk. In which component were these special correlation factors into the calculation?
So I think I understand you correctly. We do things somewhat differently in flood. So I don't think we have a similar set of procedures that we follow. But I'm not entirely sure I'm following what you do in earthquake correctly. Basically, we simulate flood hazards. We simulate individual flood events and produce hazard maps. Those would be very equivalent to your earthquake hazard maps. But then the stochastic sampling, we would look at historical discharge records, and we would look at the average number of events per year above a particular high threshold. Then, when we generated our events stochastically, we would look at the probability density function of the number of events per year and randomly draw from that distribution to determine how many events a particular year was going to get. So it would be sampled from empirical data in a stochastic way.
But spatially would be dependent on the specific hydrological basin. Yes, they will be independent.
Right.
Yes.
Yeah. So we would, the way the stochastic modeling works is you sample the number of events per year that you're going to create. You would then randomly sample a particular site within a territory to be what we refer to as the conditioning site. So that would be the place where that event was at its peak. And then we would have a correlation matrix, which shows the probability that when that conditioning site is extreme, what's the probability that all the additional sites would also be extreme? And clearly, sites close to the conditioning site would have a high probability of also being extreme. Sites further away, there would be a distance decay effect, and they would have a much lower probability of also being extreme. So essentially, it's all created stochastically from data sets. And it uses a set of methodologies developed by Jonathan Torn at Lancaster University and Janet Heffernan, which are multivariate conditional extreme methodologies.
Thank you. Yes, there are some similitudes with the approach to seismic hazards, but yes, because we overlap also fault activities and so on. So yeah, it will become, it's slightly different.
In seismics, you might use copulars.
Yeah.
But the copulars have some not ideal characteristics when it comes to flood. So we tend to use something a little more complex, and hence these multivariate conditional methods.
Thank you very much. So there is another question from Daniel Peregrina. I don't know, Daniel, are you still online? And do we want to open the mic?
Yes, of course.
Can you introduce yourself, please?
Yes, so I am Daniel Peregrina. I'm a PhD student at Deltaris and VU Amsterdam. Well, first, thank you for a very nice presentation, especially the catastrophe models part was really interesting for me. So first, to confirm, one part is, as I understood, the effect of the flood protection measures is from FlowPros is incorporated when you solve the bathymetry of the channel. And then does that mean that the model also considers downstream effects of upstream protections? So if you build a flood wall, will that change the flood wave downstream? And then the follow-up question is, how expensive or difficult is it to model, for example, new adaptation measures? Do we have to again do a full stochastic simulation to say something about what's a good or a bad investment?
Fantastic. Thank you, Daniel. Those are good questions. So we've tried over the years different ways to bring the flood defences in. Particular geographies where we have data, say the US or the UK, where we have reasonably good data on where the levees are and their heights. We've played around with building them in directly into the flood model. That will give you the downstream effects that quite nicely in the way that you suggest. Globally, and given we only have access to flow pros or supplements of that, it's much harder because we don't actually know exactly where the flood defences are, what their elevations are, and what type they are. We just know what the protection standard is. And therefore, you're right. What we do is we essentially make the channels larger in order to be able to retain that flow within the channel so it doesn't go onto the floodplain. That's obviously not exactly how that whatever flood defense is there would work, but it does give some approximation of the downstream impact. So I don't think it completely goes away, but it's imperfect and a consequence of having to do this at global scales. Actually, I've written quite a lot about how I think flood defense data is one of the big fundamental limits on the quality of the modeling that we can achieve here. And your second question about how easy is it to take adaptation strategies into account, I think the answer is actually really quite easy. The way that we've set this up with either increasing the flood channels, the other way we deal with defences is as a post-processing step. And therefore, very simply, if we change the adaptation assumptions, we could simply do a different set of post-processing and not actually have to rerun the simulation model in many cases. So I think this approach to doing defenses that we use in the global model actually makes an analysis of adaptation pathways and strategies much more feasible. And you probably know, or maybe you don't, but if you're at VU, I'm doing some work with dronettes where we're thinking about in the future doing exactly that.
Yeah, that's great to hear. Yeah, thank you very much. Really clear.
Thank you. Thank you, Daniel, also for the questions which enrich our conversation. We have a question from Adil Jouama. Adil, if you are online and you would like to pose your question, your mic should be open now. Adil? So maybe they cannot open the mic, but Adil is from Morocco, and the question is how feasible it is to map flood risk and vulnerability using water depth and water velocity data.
So yeah, pretty feasible. And that's exactly what most flood damage vulnerability functions use. Typically, they just use water depth. Sometimes there are modifiers for velocity, but no, that's unless you get into the kind of much more complex depth damage functions that people like Heidi Kreibach at GFZ develop, then water depth, most flood damage curves have water depth on one axis and relative damage on the other. So yeah, that's exactly how they work.
Yes, less common to find water velocity damage. Yeah. And it would be, I mean, from the building site point of view, only very recently we start looking at the effect of velocity and hydrostatic or hydrodynamic pressure on the failure of structural elements. So this is an area that is quite new in research as well. but not for discussion today necessarily. There is a question about, it's an anonymous attendee, so I cannot say who, but there was a similar question from MS, who has also raised their hand. So MS, if you want to speak. If they haven't left, yes.
Hi, so
Can you
great present.
introduce yourself, please?
Yeah, hi, I'm Nidish. I'm with Indian Institute of Technology, Delhi. And my question, like, first of all, I'd like to thank for this great presentation. My question is mostly related to how you develop the DEM. So from what I've had a conversation with Oliver also, so you use LiDAR data to remove the artifacts such as buildings to develop the DEM, ground DEM, and you use deep learning right now, but it was machine learning. But my question is, all the LiDAR data which is open, which you have used, is for global north, mostly Amsterdam, Australia, and also some parts of UK, Europe, and USA. And the case studies also you have shown that are also for the developed world. So how well your models will translate to somewhere, let's say in India or in Africa or global south, where the DM data is not there, or like you're using a model trained on Europe for the global south. Thank you.
That's a very good question. It's always a challenge validating, knowing how well your models generalize to places where you don't have good data. So I think it's a legitimate question. My hunch is that they'll work actually pretty well. We can compare the global DEMs that we create to ISAT data. This is quite a small footprint, high performance satellite laser data product. And we do have those data globally. So comparing our bare Earth DEMs to ISAT returns does tell us a lot about the performance of those data sets in places where we don't have LiDAR ground truth to control them. And that's where we get this 1 meter DEM error is comparison to ISAT. So I think it's pretty good. You might have seen that in the last couple of weeks, I've just published a paper on simulating flooding in Delhi. It's in Water Resources Research by Yingzhui Liu et al.
So that's quite appropriate, but I have a follow-up questions in terms of clearly the global model has been developed through Phathon, and Phathon is let's say supported by commercial ventures and commercial needs. How do you see the applications and the development at the same level of resolution, for instance, in part of the world from which you might not attract clients directly?
Okay, that's a good question. So, well, you'd be surprised where people are interested in and where people will pay for flood data. We've developed the models globally, so the data are all produced. It's just there's only some places where we can get commercial interest. However, some groups like some NGO groups are very interested. And for example, the World Bank has purchased a license for the data and uses those globally. And they also make them completely freely available in 16 developing world countries. So there's a nice list online, but it includes such countries as Pakistan, I think Sierra Leone, Democratic Republic of Congo, and a number of others. So these data are available through the World Bank for a number of places. We make the data available for academic use. And if particular countries around the world had an interest in using those data, we're very happy to have a conversation with them about what terms we could come up with that might allow that to happen, I guess would be the best way to put it.
Thank you very much, Paul. And this, I hope it answered a question that was asked about, from an NGO person that was asking about whether it's available and at which cost. So I think we can move to the next question, which is from Gabriel Betancourt. Gabriel, maybe you want to pose the question yourself. Your mic is open, I think. Gabriel? Rafael, it's the mic.
Can you hear me?
Yes, now we can hear you. Yes, please go ahead.
Okay. Okay, thank you.
Please introduce yourself.
Well, my name is Gabriel Betancourt. I work as a water resources engineer in an insurance company here in Latin America, which is called Suramericana. And I would like to ask Professor Bates some questions. The first one is, have you ever thought to include the buildings in the models that you are producing?
Sure. Gabriel, should we do these one at a time, or do you want to ask them all and I'll do them all at once? Perhaps ask them all and I'll do them all together.
Okay, the other one is if it's possible for you to explain a little bit more about how to produce the flood, the flood events that are required to calculate the losses in the model, because it's for me it's a very challenging topic that I'm still working on it, and I would like to know more a little bit. And the other one is how to manage that amount of data that is required to produce these kind of models, because you are using a climate model, you are using a topographic model. So there are some approaches. One is by tesseling, but when you do tesseling, you face the other problem, which is how to match the tessels. And sometimes I have thought that perhaps you can do this by basins, but it's the same problem because the amount of data is a lot. So that's are my questions. Thanks, Professor.
Okay, thanks, Gabriel. Okay, to take those very quickly. So buildings, we have been thinking about having building resolving models in either the next version or the one after. To resolve buildings, you really need places where you can only really do that in places where you have LiDAR data. So until relatively recently, those have been sufficiently small in number that instead it's been better to build a local model. So we built a UK model with LiDAR data, but there wasn't sufficient. And within the UK, we could have built something that was building resolving. Global terrain data sets are too coarse to represent individual buildings. But I think as the amount of LiDAR data that's publicly available increases quite rapidly, I think we're moving to a situation where we could have nested resolution in the model. So we could have 30 or 50 meter resolution over rural floodplains, but have 5 meter resolution building resolving models over cities where we have LiDAR and where there's a particular need to do that. So I think we have thought about it, and it's coming. It will have to come at some point in the next few years. It's a major computational cost. When you halve the grid resolution of these models, the computational cost goes up by a factor 10. So if we were to go from a 30 meter to a 15 meter grid, the model would take 10 times longer to simulate. And the simulation time would go from, say, 3 or 4 months to 30 to 40 months. The alternative would be to have a computer that's 10 times bigger. So that's the challenge. Flood events are created. So for the hazard maps, we simply we work out the magnitude of the river flow or rainfall that happens with a particular probability or return period. And we do that using classical hydrology that produces regionalized frequency analyses. So we take observations of river flow, we pull those together, so and we create distributions that look at the return period with how that varies with catchment characteristics using standard regression analyses. For generating the stochastic models, again, this is quite complex, but we basically look for correlations in extremes between locations. So if a location A is high, is extreme, what's the probability that all the other gauges all the other gauges in the vicinity are also extreme? So it's pretty, some of the stuff is relatively old school and some of it's pretty novel and esoteric. It is all described in the papers. So I think as a first instance, what I would recommend is having a look at that and maybe having a look at some kind of like classical regional frequency analyses in hydrology papers. That's the way to do it. And then your last question was, how do you manage the data? I mean, logistically, we have a tiled data structure. So all our data is in 1 or 2 degree tiles. The more kind of conceptual question is, just how much data is there here? And at Fathom, we're approaching around about 0.5 petabyte of data storage. So that's 500 terabytes of information in our storage systems. And that's only going to get worse. For example, we're using the SWOT satellite data for our next generation of modeling, and SWOT is generating 8 terabytes of data a day, just to give you some idea of the volumes of information we're now having to handle and process. But modern computing does make certainly in a research or consulting context, we can handle that amount of information. It's fine. We can have enough RAM memory and storage space that we can deal with files of that size. For some commercial companies, that's much more challenging because you don't necessarily have the high performance computing infrastructure that we've invested in.
Thank you. I think there is also another similar questions, but basically, yes, difficult to deliver anything meaningful unless you have an high performance computer.
Well, I mean, I say that if you're with Fathom, we have things like APIs, so you don't necessarily need to download 500 terabytes of data to be able to use this information. So you can have an API and pull in the bits of information that you need.
Okay.
Tiles over a single tile over a particular location is much more manageable. It's the kind of thing that would probably load into a GIS on a nicely specified computer workstation, which should be able to handle these data. So in practice, it's okay. And
there is the opportunity of interface with Fathom in that way, in other words.
That's correct. Yeah. So if you were licensing data or Fathom provided some data for academic use, unless you were asking for, a whole continent's worth of data, which would be quite a lot of storage, then it should be fine.
Okay, thank you very much. I think we are getting to the end of the many and interesting and very diverse questions. I think the last question is about validation again. So we are going almost back to the beginning, which is good. How feasible it is to do a quick validation of past events, which are maybe visible from satellite imagery. So use basically satellite imagery to identify a particular historic event and then validate back to find out what the depth of a particular location was or where. This is from Reinhard Magehema. If I haven't, I certainly probably haven't pronounced your name correctly, but if I haven't also misunderstood your question, please open, you will have your mic open and you can expand on it.
Yeah, thank you. Can you hear me?
Yes. Can you introduce yourself?
Thank you. My name is Reynard. I'm a PhD student at UCL in the civil engineering department. And really what I'm asking here is, can we say validate this models using satellite imagery? Certainly, because if we think about the floodplain width, I think we can get that from satellite imagery. So if we look at past events, can we sort of do a quick validation of this models based on this kind of imagery? Thank you.
Thanks very much, Raynard. So this is exactly what we've done. I've been validating inundation models against satellite data since the early 2000s. So I've done a lot of papers cleaning up satellite data and comparing it to flood models, and it's a good technique, and it has its advantages. I think the clear thing that I've learned over the years is that satellite flood images are not truth. Optical data don't see through clouds, they don't see through vegetation. Radar data do, but they have a very complex interaction with the surface. And in radar imagery, dry areas can appear wet and wet areas can appear dry. The sampling and orbit is sometimes not ideal. For example, very recently, I've been looking at the satellite information for the Pakistan floods of 2022. And actually, I think some of this data has so much error, it's actually disinformative for the modeling. Where we have compared satellite radar data to air photo observations of flooding, using this CSI metric, where instead of model and observations, we now have air photo and SAR, there we have only been able to get a CSI of about 0.75. And you would assume that air photos are pretty close to truth. Then they are not truth either, but they're closer to it than SAR. And even here, so SAR imageries are probably only 75% accurate. And that is a lot of margin for error. So your model, lots of models can fit those data to within error, and your model can be quite wrong and still be within, that gives you quite a lot of leeway to fit the model. So I think it's a good idea, but it's not panacea. And part of the problem with most people who do satellite remote sensing is they overlook the errors in the satellite observations, and they treat them as error-free when that's very clearly not the case. So yeah, nice idea, great technique, has to be used with caution. And all the time you're comparing a non-error-free model to non-error-free data.
Okay, thank you. Thank you so much.
Thank you. And I think that unless there is some last minute, very urgent questions from our audience, we can close this very interesting webinar and event. Thanking again Paul for the deep insight that he has given both in the model, and on the way in which we can use it. So thank you again in the traditional way.
Thank you very much, everyone. Thanks everyone for turning up, and thanks for sticking with me to the end. That's great.
And you will be able to catch up on the webinar on our website. Of course, this will be open for broadcast from our YouTube channel anytime. Thank you again, Paul, and very nice again for you to take the time to speak to all of us. And in a couple of weeks or 3, we will have another sessions, this time very different in terms of how it will be delivered. It will be an hands-on sessions on how do you build your own model to understand system resilience at a local scale. So we are reversing completely the point of view. Thank you again, everybody, and see you in 2 or 3 weeks' time.
Thank you very much.
Thank you.
Thank you. Bye-bye.